My name is Ingolf Wittmann. I'm running the HPC business for IBM here in Europe. And I have also the responsibility for the non-research part for quantum computing, so IBM Q within EMEA, Europe, Middle East, and Africa, because it's a nature. So quantum computing is very close to the HPC environment and to big clients in the commercial environment. What I like to do with that presentation today is a little bit to give you an imagination to think a little bit different about HPC and how this could look like in the future from the, let's say, approach side in regards of if you are a provider of HPC services, what does it mean to your infrastructure and your environments, but also from the user side to think differently in regards of their application, your applications at the end. So to take advantage of those type of technology. So let's start with that. I think everybody is aware of that problem. And even when we are talking about autonomous driving, nobody likes to have a small compute center in his back in the car. If you are going for vacation with your wife and everything is filled up, your wife wouldn't be happy. So you have to find different type of solution here. And that's also, when we are talking about these infrastructures, it's also an HPC environment. It's a small HPC environment. It's a small AI environment which is providing technology and services that you can read or newspaper or sleep in your car where your car is driving. With the current technology, when we are looking back to in the last couple of years, that was not really possible to make that happen. So we have to have different types of technology to cover that type of environment, especially when we are talking about Moore's Law. So what does it mean to, let's say, big simulations environments? So when we are running big programs in a brute force model, but also what does it mean to infrastructure type of stuff? And we have to think a little bit different how we are running these type of applications. So looking to the classical simulation environment, we are having the area of knowledge, so everything in regards of data, and we have to handle with a lot of amount of data, partly with real-time data. So when we are talking about autonomous driving, that's real-time data. If we are talking about high-speed trading in banking, that's also an HPC environment. Then we have to analyze real-time data, concurrent data, which is caused by the internet, for example, for information. On the other side, we have the experiments. And typically in the past, most of this stuff, when we are looking in the chemical environment, automotive environment, it's brute force. Just trying every type of possibility and then figuring out what's the best solution behind that. And then in the area of interference and simulations, so yeah, how to handle that, how to deal with that type of environment. And when we are looking to the total picture, typically those three areas are separate, handled, or even not in connection. And for that, as a different type of solution should be here. And we started on the Supercomputing conference in Dallas, a discussion with some of the supercomputing side, how this can look like differently. So instead of having a first approach by humans and then starting with simulations, and these simulations causing then a lot of experiments which end up in a new product. If we can turn around that a little bit, so using intelligence in that environment, so really having a look on all possibilities in an iterative way, then starting to simulate and to interfere with that, and coming then to a small amount of experiments, which is giving us then the product. That was the idea behind that, and we started small projects in 2017. Yeah, it was 2017 with STFC Hartree in that environment, how to use AI, especially here in that environment, how to use AI to be successful. And if we are talking to the whole process here around that, it's pretty obvious when we are really putting everything together and using the data in deep search with the interference and having here a model behind that, that might help us really to come down in the simulation environment. It's a complex environment when we are talking about an architecture of those type of structure, and we are talking about a cognitive discovery environment which is taking care about all the components within simulation, talking to the different types of sources of information, and then putting that in perspective and doing calculation and supporting the people who are running those simulation in an automatic way. What are the next steps for the simulation? So what does it mean? A good example is Unilever. So Unilever typically is producing care products, so like shampoo. And even there's a product development. And when we are talking about producing a shampoo, we are talking here about wet labs, for example. So the typical approach was really to use the different type of combination of ingredients and then just trying it out and pick and choose the best one. What we did is we started with some wet lab experiments, then taking those experiments, the outcome, feeding it into an AI system, and that AI system was then providing additional hints and tips or providing a suggestion what should be the next simulation, what should be the next experiment. And with that, the wet lab was going around along a certain path, which was very straightforward and very focused on the definition what the best product outcome might be possible. And what we figured out is in those type of environments, we only need 1/3 of the total compute time. We saved in the HPC environment of Unilever 2/3 of the typical compute time we need for developing such type of products. And we cross-checked it with different types of other industries, and it was really working out. So what's needed is, when we are talking about these type of environments, an HPC, classical HPC environment, and we don't care how this environment is looking like from the infrastructure side, from the technology side. And that environment is talking to a specific AI database environment where all the information about the experiments are stored, and an accelerated AI environment from IBM side. So typically we are talking here Power 9 and NVIDIA GPUs with the Power AI stack is then taking the information here out of that system. So does not have a need to know about that environment and not specifically also about the applications, but only about the data which are fed in here by the simulation environment. And with that, okay, there's some adjustments and some knowledge has to be implemented here, but with that environment, you are really able to put down the amount of simulations which have to be run to get a product or a specific solution or a specific outcome of your simulation. And I think when we are talking about HPC environment, saving compute time is saving also energy, or you are providing additional compute time to additional users in your environment. And I think that's an approach we should take into account as provider for services in those environments. But on the other side, when we are talking about big HPC environment, like the Oak Ridge environment, it's changing. So we are not talking only about, let's say, processors and accelerators like GPUs. We are talking about different type of technologies which we have also implemented within the Oak Ridge environment. And I will talk a little bit about that, how this could look like in the future. Why is Oak Ridge interested in that? Because when we are talking here about that environment, that's pretty big. So it's 200 petaflops. But how to become really an exascale system? With traditional compute environment, I think that's really hard to achieve, or you have to have really a big energy bill, because we are talking here about 30 megawatts of power. But also it's 10,000 processors we are having here. We are talking about roughly 30,000 GPUs in that environment, and 250 petabytes in storage, 340 tons of weight, 520 square meters in floor space, and last but not least, 50,000 liters water to cool that environment. So that's really not scaling. So if we like to double the performance of that environment, we have to think a little bit differently how to make that. So if we are looking to the current environments, typically we are using to provide these HPC environments, most likely from the IBM side, Mellanox as fabric. In the AI environment, we're starting with FPGAs, but also with NVIDIA as accelerators and flash systems for the information. The processors are limited meanwhile. So we are talking about mainly 3 types of architectures, but all of these architectures having their limitations. And there are only small areas where we can think about what to do and how to do differently, and I will introduce some of them. And the hope is here in that environment. So looking on that, we will have for Neumann architecture in the classical environment, and that's moving slowly forward, but we will have some improvements. The main improvements will come here out of that environment. And if you are talking about for Neumann architecture, okay, we can think about 3D chips, but those are really producing a lot of heat when we are putting several layers of processors over each other. That would cause some big problems to get rid of the heat in those environments, and we have to think how to do that. One opportunity here is to put light into the chip. So instead of having power for communication, using light optotronics technology, we developed in our research labs the first samples of that, and that's working very fine, because light is not producing any type of heat, and it's pretty fast, and you can scale that down very much. On the other side, if you are talking about 3D chips, we have to talk also about water within the chip, not on the chip, or cooling memory DIMMs on the DIMMs, but within those chips. It's difficult because of the sizes, but the advantage is you can run those environments by a higher temperature as classical computing environment, even water-cooled environment we are knowing today. And different type of technology is 5D. And 5D is quite something very interesting, which is helping also, or maybe also a solution for the non-von Neumann architecture type of technology. So why 5D? What do you guess? 2D is the chip. So if you are talking about the chip, that's 2D. 3D, so we are stable the chip. So many chips each other. 4D is the power. So we are talking here about a specific possibility how to power that chip. And that's not done by electricity. It's done by a fluid which is going through the chip, and it's having a battery capacity. So it's taking the same material, more or less, like you have in batteries, and that's electric loaded and giving source electricity to the chip. And 5D is, okay, that fluid you can also use for cooling. So with that, you have a fluid which is powering up the chip, but also cooling the chip. And the first samples we built is, so those are able to power a 10 milliwatt chip, so that's not very much. So compared to a GPU or a big processor, but might be a possibility for new neuromorphic devices, and I will talk about that in a minute. And those environments can be really stacked. So we can think about brain-inspired computer which are stacked and packaged, very dense, and providing a good performance and good compute power by a square meter or cubic meters. Okay, but that's all what we can do in the processor environment. And I think that's not really helping us to overcome with all the problems and to get an exascale system at the end. So there's something additional what we have to take care about. And there we are talking about non-von Neumann architecture. That means a totally different type of architectures, of programming, of using those environments. And it's quite interesting to see how these first attempts are looking like. So when you're looking at this lady, and I can use that picture somehow here. If I'm doing university lectures, the students are not knowing that lady. And for that, I have to go for that guy. Okay, so everybody at least is knowing that guy here. And so it's a cognitive process which is happening in your brain. So it's a certain amount of compute power. You are seeing something, you are recognizing it, and you're getting a name or vice versa. And that's done by your brain on a very interesting way. If we are talking about cognitive computing, we can really use that type of method also in classical computing environments. And that's the thing what we like to do and where research is going on. And the reason for that is even big GPU environments are very cost intensive. And if we are talking about big HPC environment from the price side, when we are talking about how the system should look like, the processor and the rest of the infrastructure is less from the price than when we are putting additional GPUs here in those environments. So there must be something different from the price side, but also from the energy side and how to program that. So we are talking here about neuromorphic computing or brain-inspired computing. So its classical processor is typically with zeros and ones, and it's fed by data. It's a classical, we are talking about classical von Neumann architecture. When we are talking about the other side, so the brain-inspired stuff, it's sense act, it's symbolic, it's simultaneous in a certain way. Quite different to the classical computing. It's in a sequence, it's in a batch, and it's low power. And that's a very important point here on that. And IBM was building with the DARPA project a couple of years ago, so-called a specific chip who is having exactly these type of capabilities. And we are able to build neuronal networks with hidden networks which are behaving like a human brain. based on math. So if we are talking about neuronal networks, so those of you who are familiar with that, that's the equation for that. When we are talking about spiking method, so how neurons are behaving. And what we figured out using that chip here, classical processor is having a speed from 1. If we are talking about NVIDIA processor, we have a speed up by 20. If we are talking about FPGAs and specific solution in those type of environments, a speed up of 100 is possible. And if we are talking here about that Synapse chip, it's infinite. So if we are doing pattern matching, recognition, this type of stuff with that chip, it's just there. And the nice part here is it's really like a human brain, because we are talking about programmable neurons and synapses and cores, and there's no clock. So it's information is coming in, and we're compute, and something is coming out. By a trained neuronal network. That's the idea behind that. And only those parts who are used are powered. So that chip is using 70 milliwatts. So it's a mobile device. So it's a good opportunity for mobile devices to do speech recognition, for example. So the current speech recognition for Apple iPhones or the Android iPhones, so it's limited to the processor you are having into that mobile device. So using that device here within a mobile device, you are not anymore have to use to touch on your screen. You really can talk directly to that. And that's one of the projects, pilot projects we are doing actually with Apple and with Samsung to use that chip in that environment. But that chip is also used in the Oak Ridge system. A couple of racks built in with some thousands of these chips to do pattern matching, pattern recognition in that environment. So that part is not part of the, let's say, counted 200 petaflop compute power environment. If we would add that, the 200 petaflop would increase by a certain amount of number of additional petaflops, but we cannot do a linpack or run a linpack here in that environment. And the reason you will see in a minute. So the idea of that chip is to use an external environment where we are training the neuronal network with a compass simulator, and when that neuronal network is fine, then we are putting it into the chip or the whole environment, and it's like an EEPROM. The nice part here is for autonomous driving, no self-learning, so nobody can change the system. So it's that what you are expecting, hopefully, to get out of it, you will get out of that type of environment. That's the reason why Bosch and automotive companies are interested in that environment. And you can use that with, say, one chip, but also a couple of chips if you are building up bigger neuronal networks. The approach is pretty easy, simple. That equation is here in that environment, and we have also the leaking information, which are in neuronal networks typically causing built in. And here are the input parameters, here are the different synapses, and then you are getting the output of the systems. For example, when you are try to recognize traffic signs and get an immediate feedback for autonomous driving. Not everybody likes to implement everything from scratch, so what we provide is certain libraries for that environment, for speech recognition, for picture recognition, but also for the autonomous driving collision avoidance system. So those libraries are already there and can be used for the training environment, for the compass simulator, and then put into the system. And this is an sample for the next generation we are looking forward. So it's an 8 EU system filled up with these chips and providing the environment for those type of neuronal networks. Another solution is using FPGAs. So with the Synapse chip, we are talking about spiking environments. So that's one very specific environment, but you really cannot have every type of solution, and sometimes you really like to have also a self-learning system, so for deep learning or machine learning, and with that you need a different type of technology, and that's what we built with Escape. It's based on an ARM processor and a certain amount of FPGA and a certain amount of memory. And this is one node, and 27 nodes are built on one card. That's the smallest environment. And you can train that system. You can run it also as a self-learning system in such type of environment, and you can make it bigger. So with one drawer, with one cage, you build in 16 cards and having then there 432 nodes of that. The first sample we implemented in Jülich, so we installed that in December last year as a test case, how this is working in an HPC environment or in an AI environment, and to get first, let's say, experiences for these type of systems and how to integrate it. In 2019, we like to build bigger systems. And the nice part here is we are talking about simple, let's say, components. Those are not very expensive. And that means we can build also big AI systems based on a very decent price tag. And as already mentioned, we can use that also for the self-learning environment in specific solution scenarios to use that type of technology. And that's pretty much forward to be integrated in a normal infrastructure environment. So if we are talking about the future for those type of solutions, then with GPUs, with the Synapse, we do have some solutions. If we are talking about efficiency, then we are looking forward for more efficiency, especially in the accelerated environments for deep learning, using specific technologies here. And for big cloud environments, for example, for permanent learning, building up system environments, that's really something for big compute environments. Okay, last but not least, and I was talking about my second mission. It's quantum computing, and we are talking here about quantum computing because that's really giving us a speed up in some areas, some specific areas, which are incredible. And that's the first time, to be quite honest, that as IBM, I do not have to reach out clients reaching out me. And we are invited to many sessions to talk about our solution and what we are providing here. And the nice part is everything what we are doing here is open source. So it's public available and can be used from everybody. Just a short wrap up, what does quantum computing mean? So in classical environment, we are talking about normal bits, zeros and ones. And it's a silicon structure, maybe 7 nanometers, 14, or something like that. But the difference from the compute side is you can run these type of environments as long as you have power, and those systems are powered up in a normal temperature environment. So as long as you can cool that down, everything is fine. Quantum computing, we are talking about quantum mechanics. And we are talking about manipulating electrons, photons, or very pretty small environments. And we are talking from the IBM side here really about copper electrons or pairs of copper electrons. And to manipulate those, we are talking about environments which have to be controlled. And to be controlled and to control these electrons means we have to cool that down. Otherwise, there's no possibility to define the energy state, so where on that orbital the electron is. So that means we cool down those environments to 50 millikelvins. So that's cooler than space. But that environment is not very stable. So we are talking about a compute time of 100 milliseconds. So all your computation has to fit in that time. Otherwise, the outcome is having too many errors that you are not really can say, okay, there's something which is giving you an advantage. The difference between those two environments is if you can use the quantum mechanics effects, and I will not go into the details, so means putting two qubits together. So one qubit is the smallest amount of compute environment within a computer. If you can entangle those 2 qubits, then you have 4 states which can be calculated at the same time, where you need here 4 different steps to compute that. And that's really the power of quantum computing at the end. Also, the difference here is we do not talk about, let's say, programs. We are talking about problems which are defined in a mathematical way, which are defining all possible solutions and then calculating down the solution to hopefully one outcome. That means quantum computers are part of classical computing environment because those are very specific and tackling only specific environments within the HPC computing environment or traditional computing environment. That means zeros are getting in and zeros and ones are getting out. So you have to see a quantum computer as an accelerator in such type of environment. Where are those areas? We are talking here about mathematical problems. So everything what with linear algebra, with Hamiltonian can be expressed, might fit in those environments. And we are talking about medicine, materials, machine learning, search of big data, which might benefit from the technology. And how is the technology looking like, or those environments? 15 millikelvins, that means the processor is below here. You have to cool that down. That takes you 48 hours. So 48 hours to cool that down, and then you have to calibrate that environment, and then you can start to run that environment. What we provide is a cloud environment. So we are providing for every user who like to access an IBM Q system and a cloud environment on your laptop. You can download also the Qiskit environment, the IBM Q experience environment on your laptop, doing your programming here, then starting your program. The program is going to a classical power system. It's a Power 9 system, which is translating your code in microwave signals. The microwave signals are adjusting the energy level of your qubits. So putting superposition, entanglement, rotation of your qubit. And then when all the positioning and everything quantum gate operation are done, then you are doing the readout. And because you really cannot read out the energy level of an electron, so you have to use a trick. You raise the energy level, and that means on a certain point you can say, okay, it's a 0 or a 1. And with that, you're getting back then to your system 0 or 1. And you can integrate that environment in a classical Python environment. That's the environment what we are providing. That means you can integrate that in every type of IT infrastructure you are running. So we did a lecture at the University of Osnabrück where we used a Raspberry Pi for pattern matching recognition, which was handing over then to a Watson system who was doing some analysis and then handing that over to the quantum computer to do the calculation. It was a modulo 5 problem, and then getting back the feedback from the system with zeros and 1. And you can do that iteratively. So that means if the size of the quantum system with 20 qubits, for example, is not big enough, you can formulate your problem in an iterative way. That the classical system is then doing in an iterative way, finding out the solution with the quantum system together. What are the possible application use cases where we are thinking about? It's physical science and chemistry by nature, because quantum mechanics is about chemistry, about atoms, this type of stuff. So by nature, that's fitting very well to quantum computing. With that, also optimization is a very interesting path. And when I'm talking to clients, actually, the biggest interest is banking. With risk analysis, for example, Monte Carlo methods, and the oil and gas industry. Those are interested here in those environments. I was expecting in Europe the automotive environment, but we started with Daimler, and we are still talking to the rest of the automotive industry. But really finance and oil and gas, those are the most interested industry environments. And then artificial intelligence in a totally different way, because we are talking here not about a huge amount of data you can load. You have to formulate your problem and then to bring in the problem within the IBM Q or the quantum system. If you would have quantum sensors or quantum memory, then it would be a different thing, but actually building up a solution approach means building up the quantum system with the problem. Then the coherence time, the 100 milliseconds is over, and you do not have any time to calculate. So that's a little bit far away, but if we can extend the coherence time and build bigger systems, then this might be a good solution also in that type of environment, because the approach is to work with limited amount of data. So far less data which you which you need in a classical neuronal network environment. The other part is really when we are talking about simulation, and you can run the IBM Q simulator also on your laptop, on power cluster environment. And when I'm using my laptop, it's a 20 qubit system. So that's the power of a laptop. If we are talking about a 2-node Power 9 cluster with GPUs, we are talking about 30 qubits roughly. If we are talking about the Oak Ridge system, we are talking about 50 qubits. So you see how this is scaling. So every qubit you put additionally in such type of environment is doubling your memory amount and your processor amount you need to simulate such type of environment. And GPUs are having a very positive effect here in such type of environments. So to simulate the noise, the errors in such type of system, but also giving you the advantage to build additional qubits besides the processor and memories, and to increase roughly maybe 1, 2, 3 additional qubits and in such type of big environments like the Oak Ridge environment. And we used the Oak Ridge environment for that. And Oak Ridge was showing, not only with the simulator, but also with the AI environment, that type of environment is scaling linearly. So the more nodes you are adding, the more compute power you're really getting out of that. And that's something unique with the Power 9 architecture we built here with the Summit system. So everybody who like to get access to that, just Google IBM Q Experience, log on with your Facebook account or Google account. You can start lectures, you can start tutorials, you can run programs on the simulator, but also on the real system. And for those guys who like to dig deeper, we built the IBM Q network, where also things of stuff is defined like IP stuff when we are talking about real problems and real solution in such type of environment. And for the IBM Q network, I might be a good entry point if you like to have this type of discussion. So there's a huge amount for our systems, and we have to really bring them out of the lab to build it in an industry style, with industry components. And that's the IBM Q System One, which we announced in January this year. So it's the first commercial reproducible system with 20 qubits, and everything is here in that system. So here's the Qgraph, here's the 20 qubit chip, and behind here in that rack is all the cooling technology with helium-3 and helium-4, all the microwave generators, and that's technology which is developed in the Böbling lab in Germany, for example. So parts of the development of the IBM Q system is also in Europe, not only everything in the US. And also the other components which are needed are part of that. So that means the bring up is pretty fast, because you just have to move that glass cubicle with all the components and then plug it on, and then you really can run it. We built up our first compute center in Poughkeepsie, in northern part of New York. And we are talking up because every member in the IBM Q network is getting access and getting specific compute time for those systems. So we need many of them. So we produced a certain amount of these systems already. And that means, so we really have to have a separate compute center for those systems. And we are thinking about to build something also here within Europe for the quantum flagship project and for cooperation with European customers. So, talking about how the infrastructure is changing, I think we are pretty much aware of that. There will be some small changes in the processor system environment. The big changes will be here. And those systems are connected in different ways to the HPC infrastructure environment. Some of them do not need very fast and very low latency connection like the quantum technology, even the neuromorphic systems. We are not talking about huge amount of data which are putting through. So it's pretty easy to really integrate those type of technologies in those type of infrastructure. What we have to learn, and that's a call for the applications people and the programmers, the libraries and the programming environments are available. And most of them is provided by IBM open source, like the quantum technology. Get familiar with that and really have a look which part of your application can benefit from these new types of technology and the overall architecture here in such type of environment, using also AI in the simulation environment to reduce the amount of simulations which have to be run in such type of environments. And with that, I think I'm finished, and hopefully you get an impression how the future can look like and what type of technology you can face in the next couple of years. Thank you very much.